Good morning, student. Today we are going to learn about frequency shift keying, that is FSK. After the completion of today's session, you are able to define frequency shift keying, explain the generation and detection process of frequency shift keying. So FSK is the digital modulation technique in which the frequency of the carrier signal varies according to the digital signal. The simplest form of FSK is binary shift keying. So today we are discussing about BFSK. Okay, binary frequency shift keying. So these are the waveform. So in this figure, the first waveform is the modulating signal in the form of the bit stream. Then the second two means the second waveform and third waveform. The second waveform is the high frequency waveform and the third waveform is the low frequency waveform, and both are the carrier signals. In FSK we use two carrier signal. Okay. Then the last one is the modulated signal. So this modulated signal is the frequency shift keying modulated signal. Okay. So if someone give you a digital sequence, then you can easily draw the BFSK waveform. So if this signal is given, then here you can observe that, see here, when 1 is given, we get a high frequency signal at the output as the cycles are very close to each other, and when the 0 is given, at that time the spacing between the cycles are quite wide enough, means more. So when 0 is given, at the output we get a low frequency signal. Like this, for any bit stream we can easily draw the BFSK waveform. So just draw the dotted lines. Then for 1, draw the waveform close enough. For 0 it is wider. Then for 1 it is close enough, like this. Okay, you can understand, draw it properly. Here it is not possible to draw. Okay, next one is the generation of FSK. In this diagram, when we give 0 at the input, then here 0 is given to the multiplier, but here the 0 is given to the inverter circuit. So at the output of the inverter we get 1. As we discussed earlier that two carrier signals are used. One is the high frequency carrier signal, another one is the low frequency carrier signal. If this one is the high frequency carrier signal and this one is the low frequency carrier signal, then here we get cos omega 2t. But when we multiply 0 with this carrier signal, here we get a 0 value. This one is the adder, so at the output we get a low frequency signal. Okay, then when we apply 1, then here 1 is given and here 1 is given to the input of the inverter, and at the output of the inverter we get 0. So anything multiplied with 0, at the output we get 0, but here we get cos omega 1t. We know that omega means 2 pi f, so here I write omega 1t. So at the output we get cos omega 1t, means anything added with 0, the same thing we will get at the output. So cos omega 1t means this one is the high frequency, as we assumed earlier that this one is the high frequency and this one is the low frequency. Like this the generation process works. Next one is the detection technique. Similar, demodulation means recovering of original signal from the modulated signal, and there is two types of detection technique, that is coherent detection and non-coherent detection. Okay, first one is the coherent detection. As we know, coherent means where synchronization is required. Same carrier signal is used in both transmitter and receiver section to provide synchronization. So it consists of two integrator, two multiplier and one decision device, or mixer, we can say this as mixer also. So BFSK waveform is fed to the mixer along with the two separate carrier, that means that is used previously in the transmitter section. The similar carrier is used here. One is the high frequency carrier, another one is the low frequency carrier. Then the output generated by the mixer is fed to the integrator. The output of the two separate integrator is then compared by the decision making device. When the output of integrator 1 is more than that of the integrator 2, then the frequency of the carrier generates the 1. Then similarly, when the output of the integrator 2 exceeds the integrator 1, then the carrier frequency associated with this correlated to, because the combination of mixer and integrator is known as correlated to. So frequency associated with correlated to generates symbol in favor of that frequency. Like this we get 1 or 0. Okay. Next one is the non-coherent detector. Non-coherent means where synchronization is not required. So in this diagram you can observe that no carrier signal is used, and the circuit consists of, or the block diagram consists of, two band pass filter, two envelope detector and comparator. So two separate band pass filter tuned to different frequencies, means both the band pass filter having different center frequency. Okay, then the output of this band pass filter is then fed to an envelope detector, which generates two separate output according to the signal given by this band pass filter. Okay, then this comparator compares the output of the two envelope detector. When the output of detector 1 exceeds detector 2, the logic 1 is obtained, and when the output detector 1 is lesser by or exceeded by detector 2, then logic 0 is obtained. When detector 1 is greater than detector 2, then 1 is given at the output. When it is detector 1 is less than detector 2, then 0 is given at the output. So this is all about frequency shift keying. Thank you.